use a clean finger. What? No such thing. What he found was that everywhere he looked, the stars did not have the same spectrum as here on Earth, but they had the same holes where the hydrogen had absorbed the light and then re-emitted it. And because in quantum mechanics you're limited to certain levels, would somebody be wonderful and get me a glass of water or something? Maybe I'll get water in my can. Forgive me. Okay. So, they called this a redshift because the missing holes were moved towards the red. And what Hubble found was that by using the type 1 supernovae as their standard candle, I'll erase that, it's on your handout. He could make some hypotheses, and the first hypothesis that he came up with was there was a relationship between how much redshift and how far away the star was. So if you have our star, which is red, and you got other stars that are at different distances, and this one, if this one goes supernova, boom, sometime later the light will get to us. The star may actually be gone by the time the light gets to us. But as it travels, should I say that now? As it's traveling, it appears that the distance is related to the velocity. So the distance d, not velocity, is proportional to a change, which is designated as delta. I'll put it, as that wavelength comes to you, the space which is traveling through appears to be expanding. And so while the wavelength starts out on your balloon, where's the big balloon? Did it bump already?
It's here.
I'll put her.
Big guy. Okay. Okay. This is the universe as we know it today, supposedly. Nice universe. Sit. Don't go near Pepe. He's got sharp things. This is one that was blown up and then rewritten on because it wasn't legible anymore. But if you imagine what he's saying is that the farther away a star is, the faster away it's moving, because the redshift that I mentioned is related to the fact that it's moving. And you have to have a frame of reference. We use our solar system as our frame of reference, or the sun alone. I don't know what physicists actually do use, but I believe that's probably true. So if you look at Earth's timeline and make a guess for how old the Earth is, or excuse me, how old the universe is, you can use this equation of things expanding. Now, there are three possibilities. It expands and continues to expand as it is currently, forever. And what happens then is you end up with so few particles per cubic meter that you essentially have nothing. You have empty space with maybe 100 atoms in each cubic meter, if it extends, if it's infinite, or if it has an infinite age. There's a interesting book to read where he makes the claim, I think it's in this one, where he makes the claim that where he explains the claim for the Big Bang or the Big Crunch. So 3 possibilities. It could go on forever, or it could reach equilibrium like something that's elastic and then come back. And that would create what's called the Big Crunch. So, you see what happens to the... I need volunteers. Okay, so if you're the modern universe, and let's say for whatever reason we're at that equilibrium point, which we're not, and things reverse, and you get a big crunch. This is what happens. The wavelengths are, see the red wavelength and the red wavelength? Let's pretend they're the same. Okay, that was fun. Well, actually, now I can use this one as the... because I was about to let its hair out. Anyway, I brought extras. That's all right. Okay, now, okay, we've got our nice big red wavelength. We'll look at what has happened to its frequency. Wish I could just cut that off. Anybody got a knife on them? But look at what's happened to its frequency. It's much smaller. It's much tighter. And so if something's coming toward you, you'll get a blue shift. And ultimately, people don't know, but their guess is that it's possible that what we're seeing... Marlene, thank you, sorry. Is it Arlene? Marlene.
Marley.
Marley. Okay, sorry. Stay, please. And there's the comparison. Stay! You may notice also that balloons pick up electrostatic activity very, very quickly. And that's one of the forces. So what forces do we know about? We know about an electrical force, sparks. We know about magnetic forces. We know about gravitational forces. And we know about physical forces, that is work, kinetic energy, potential energy. If I lift up the ping pong ball that doesn't have water in it, it has potential energy. If I had an egg down here, and let's say this was a lead ball, and I dropped it on it, it would convert its kinetic energy, its height plus its mass, or times its mass, I believe. Anyway, acceleration and mass. There's an equation, which you probably have seen. Plus a squared prime plus b, oops, a c. I am really having trouble pulling things out today. 1/2 at squared plus bt plus c is equal to e. Okay. What does that mean? What it means is that you can make calculations ignoring the c, and you can turn this, you can get, because it turns out, if you're looking at things that are very, very old, or the distance is very, very far, no matter what this c is, unless it's ridiculously high, you can use that formula and others to get the other information.